The civilian understanding of stealth aircraft rests on a persistent myth, the belief that these machines are simply invisible to radar. This is a fundamental misconception. In this explainer, we will dismantle that illusion. The engineering reality of stealth is not a magic trick. It is a precise, calculated manipulation of the cold laws of physics, designed for one singular purpose: survivability in hostile airspace.
Radar systems operate by transmitting electromagnetic energy and reading the reflections that bounce back from a target. Because physical matter occupies space, physics dictates that an aircraft can never produce a radar return of zero. Stealth, instead, is an exercise in radical mathematical reduction. Consider the scale. A standard commercial airliner presents a radar cross-section of roughly 100 square meters. A conventional fighter aircraft like the F-16 returns about 5 square meters. The F-22 Raptor, however, reduces its signature to exactly 0.0001 square meters. To an enemy radar operator, this 50,000-pound warplane registers as an object the size of a steel marble.
The foundation of this reduction begins with System 1, airframe geometry. On a stealth platform, aesthetic design does not exist. Every contour, every angle is dictated entirely by the mandate of survival. Conventional aircraft function essentially as flying corner reflectors. Their 90-degree vertical fins and flat fuselage panels bounce radar energy directly back to the transmitter. The F-22 eliminates these structures through strict edge alignment directives. Every leading edge, trailing edge, and panel gap is oriented to a highly restricted set of discrete angles. When incoming radar energy strikes the airframe, it is not absorbed here. It is deliberately deflected away, scattered into calculated, harmless directions that the enemy receiver will never see.
Yet physical geometry alone cannot hide everything. This necessitates System 2, radar absorbent material. Certain structural requirements, such as engine inlets and canopy frames, inherently trap radar waves. Where geometry fails, engineering relies on a secondary layer of defense. Radar absorbent material, or RAM. Applied precisely across the aircraft's external surface, these highly classified, iron-impregnated compounds engage radar at the molecular level. When electromagnetic waves strike the coating, they induce microscopic electrical currents within the material itself. This reaction instantly converts the incoming radar energy into trapped, dissipated heat. The enemy's signal arrives at the aircraft, but it is destroyed before it can ever return.
This capability, however, carries a severe operational cost. Stealth is not a permanent state. It is a highly fragile condition. The specialized RAM coatings are incredibly sensitive to temperature extremes, atmospheric moisture, and the sheer friction of supersonic flight. Take the B-2 Spirit bomber, for instance. It demands massive post-flight hours from dedicated ground crews. After missions, technicians must meticulously inspect the airframe and manually reapply the coating to any degraded sections. Without this constant intervention, the aircraft's radar-evading properties quickly fail. The physical aircraft is now concealed, but its internal machinery is not. This brings us to System 3, signature management.
Airframe geometry and radar-absorbent coatings cannot mask the violent mechanical operations of a jet aircraft. To survive, the platform must control its own emissions. Signature management executes 3 critical steps. First, the highly reflective spinning blades of the engine compressors are hidden deep within the fuselage, masked by continuously curved, ram-lined inlet ducts. Second, all munitions are completely sealed inside internal weapons bays, exposing themselves to enemy radar for only the fraction of a second it takes to launch. Finally, the extreme heat of the jet thrust is managed. Slotted exhaust nozzles rapidly mix the exhaust with ambient air, dispersing the thermal plume and severely reducing the infrared signature that modern heat-seeking missiles rely on.
We now turn to a critical vulnerability, the low-frequency radar threat.
There is a specific operational limitation to stealth technology that standard military briefings often choose to obscure. Stealth platforms are highly optimized to defeat high-frequency centimeter wavelength targeting radars, the kind used by surface-to-air missiles. But low-frequency radars, operating in the VHF and UHF meter bands, interact with physical objects much differently. The absorbent RAM coatings simply lack the physical thickness required to trap these massive, elongated waves. Modern air defense systems, such as Russia's MEBO-M and China's YLC-8B, are purpose-built to exploit this exact physical loophole. Operating in these lower frequencies, they absolutely can, and do, detect stealth aircraft.
This reality presents a stark tactical question. If adversary low-frequency radar arrays can successfully illuminate an F-22 Raptor, Why does the platform remain so dominant? How does a detected stealth fighter actually survive in heavily contested airspace? The answer requires a fundamental paradigm shift. We must distinguish the act of detection from the act of targeting. A low-frequency radar system acts as an early warning mechanism. It alerts an enemy operator to a presence in the sky. However, because its wavelengths are so massive, it fundamentally lacks the precise angular resolution required to actually guide a surface-to-air missile. The enemy operator knows the aircraft is in the general vicinity, but they cannot generate a mathematically precise coordinate to feed to a weapon system. This is the core truth of the engineering. Stealth was never designed to be undetectable. It was designed to be untargetable.
The ultimate outcome of uniting these three engineering systems, edge alignment geometry, radar absorbent material, and rigorous signature management, is not absolute invisibility. Instead, the outcome is an engagement window so severely delayed that the stealth aircraft completes its mission and releases its ordnance long before the enemy defense network can compute a targeting solution. But as global low-frequency radar arrays grow exponentially more advanced, we are left with a critical operational question. How long will this mathematical advantage hold before the fundamental architecture of stealth must be entirely reinvented?